Hello, everybody. I hope you're doing well and staying healthy and safe. Make sure you wash your hands all the time, guys, and don't touch your face. And follow the social distancing as they have told us. Okay, guys, so this is my first video, as I promised you in the email that I sent you, I guess, yesterday. Today is Tuesday. It's about 3:30 in the afternoon, and I just finished making videos for the other two courses that I'm teaching at Wentworth, and now I'm getting to your course. So you guys remember the last thing we did in the class before the exam, and I'm sure by now you got your grades and everything, and hopefully at some point, if I go back to my office, I'll just make a copy of the solutions and email it to you. But anyways, you guys remember we started chapter 6, talk about shear and bending moment diagram, and now we also started talking about the stresses due to bending. So just a quick review here, guys. So you guys remember that if you have a section of the beam under the action of a bending moment, this would be, by the way, a positive moment. Remember, happy face, sad face. This would cause the beam to be happy. So this is the front of the beam, and this is the cross section right here. So this is the cross section, right? Which I'm just taking it to be rectangular. Okay, so remember that right on the neutral axis, sigma is equal to 0, because the strain is 0, epsilon is 0. Therefore, sigma is 0. So if you had whatever length you had here, you were looking at a piece here. As this guy bends, this length doesn't change. So if the length doesn't change, epsilon is 0, therefore sigma is 0. Okay, so stress becomes maximum in the top fiber and bottom fiber. Compression in the top fiber, right? The same thing, of course, you have over here. And tension in the bottom fiber due to a positive moment. Okay, so the general equation known as Flexure Formula is equal to sigma equal my over I. Y is what? Y is just the distance from the neutral axis, the neutral surface, to any position. But since we want to find usually the maximum moment, maximum stress rather, sorry, we'll go to the top fiber. So maximum stress will happen right here and right here, in the top fiber or in the bottom fiber. So instead of Y, we put C. So sigma max becomes MC over I. You guys recall that I did actually a derivation for you, and I showed you for a solid rectangle, right? Solid rectangle. The moment with the width of B and a height of H, or the depth of H, the moment of inertia becomes 112 BH cubed with respect to the neutral axis. Now I thought maybe I was about to talk about, before we were done on that, I believe Tuesday before the break, I wanted to show you how we could easily find the moment of inertia of an I-beam, and we ran out of time. So let me show you the moment of inertia of an I-beam. I'll just show you just a quick example of a beam with a very simple loading and how to calculate the bending stress. Then I will come back with another video quickly and show you how you handle unsymmetric cross-section. So remember, an I-beam is a symmetric cross-section made of two flanges. So these are the flanges here, right? Two flanges, and you have the web in the middle. And that's the web. The red is the web. Okay, I gave you this dimension so we can do a problem. Now, how would we go about finding the moment of inertia for this beam with respect to this x-axis or neutral axis? You can call it even x-axis. Guys, look, the moment of inertia for a rectangle is 112 BH cubed. Why don't you think of this I-beam as a full rectangle of dimension 6 by 8. You see, the depth is what? 8 inches, right? 1, 1, 1, 1, and 6, right? And then you have to take out what? Two pieces, right? The piece over here and the piece over here, right? But if you push these two pieces together, isn't that this piece together as what? If you subtract a 1 from the 6, this becomes what? A 5 by 6, right? And look, the axis, the neutral axis, actually is right on the middle and matches for the two. So we can say, oh, I sub x then is 112 BH cube for this guy minus 112 BH cube of this guy, because we're subtracting, right? So why don't we factor the 112? What is B? B is 6, H is 8 for the first rectangle, the black one, minus what? BH cube 5, 6 cube. Here we go. You can put parentheses around this if that bothers you. So this comes out to be about 166, or exactly 166 in fact. Remember, the unit is what? Inches to the power 4. All right, now imagine if you had a beam, right? Let's do a problem. You had a beam, it was cantilever. You had a uniform load acting on it of, say, magnitude of, say, 600 pounds per foot, right? Over what? Over, let's say, 10 feet. And let's say the cross-section of this beam was this guy, this I-beam that I showed you here, for which the moment of inertia is 166. And my objective is to find sigma max. Now, you guys know that the maximum bending moment for a beam like this will happen, obviously, right here. And that maximum moment can be easily determined by just finding the moment of this distributed load. Remember, the distributed load could change. You could change it to a 600 by 10, and then you would multiply it by, so 600 times 10 times 5 feet. And that comes out to be 30,000 pound-foot. Just be careful with the unit. Right away, change that, multiply it by 12, so it becomes 360,000 pound-inch. Because remember, these dimensions are what? Inches to the power 4. All right, we're ready to calculate sigma max. So sigma max is equal to, based on the Flexure formula, maximum moment times C over I. Maximum moment is 360,000. Let me carry out the unit for you. Pound inch. Times C. What is C? C is the distance from the neutral axis to the top or bottom fiber. Doesn't matter. The top fiber, by the way, this one would be a negative bending. See, this beam would bend what? Which way? It would bend like this. So top fiber would be what? In tension, and bottom fiber in compression. So in the top here, tension, in the bottom, compression. Right? Okay, so what's C? Half of the depth, half of 8, 4 inches. C becomes 4 inches. So 4 inch divided by I. 166 inches to the power 4. Take a look at the unit, guys. Should come out to be PSI. And this comes out to be roughly 8,675 PSI. Now imagine if this beam was made of wood, it wouldn't be able to take it. Maybe the best wood can take, I mean, like a pine, a very fine Douglas fir pine can take maybe 2,500 PSI. But if this is a steel, say A36, remember, the yield for a steel is what? If it was A36, the yield is 36 KSI. So this is way below. This is only 8.6 KSI. So this is way below that. So this is safe if this was made of a steel. All right, guys. So remember, all the communications are done through email during this time. By the way, just a funny thing, I'm calling these videos Corona videos, kind of. I know it's not funny, but hopefully we'll go through this safely, and nothing bad is going to happen. So stay safe, guys. Stay healthy. Remember, don't get too close to other people. Wash your hands all the time, and I'll come back with another video. Okay? Thanks for watching and listening.